We have problem number 13 in advanced classical mechanics practice final exam. So let's consider a free particle in one dimension where L is 1/2 mx dot squared, and the transformation x maps to x plus epsilon t, and t maps to t, changes the Lagrangian by a total time derivative. So for letter A, show explicitly that the action is invariant up to a boundary term. Letter B, use Noether's theorem to find the conserved quantity. Letter C, interpret the conserved quantity physically. Letter D, compare the symmetry with ordinary spatial translation symmetry. And letter E, explain why total derivative changes of the Lagrangian do not affect the equations of motion. So this is a Noether symmetry beyond point transformations problem. So the free particle Lagrangian is L equals 1/2 mx dot squared, and the transformation here under an infinitesimal Galilean boost, Galilean boost, sorry about that, is x maps to x plus epsilon t, and t maps to t for that Galilean boost. So the infinitesimal variation is delta x equals t, and delta x dot equals 1. Forgive the poorly constructed deltas. The variation of the Lagrangian is delta L equals the partial derivative of L with respect to x dot. Delta x dot equals m x dot. Okay. However, mx dot equals d dt mx, and therefore from here delta L equals d dt mx. So what we could say is the Lagrangian changes only by a total derivative, and the action changes by a boundary term. And here we have that delta s equals that integral from t sub 1 to t sub 2 delta L dt, and that's going to equal the integral here for t sub 1 to t sub 2 of this d dt mx dt, and that's going to be mx t sub 2 minus mx t sub 1. So the equations of motion happen to be unchanged. Sorry about the grammatical error there. Okay, so that is the first component of this, building on that. So what we could say is for a quasi-symmetry with delta L equals derivative of f with respect to t, Noether's conserved quantity is q equals p delta x minus f. So here p equals partial derivative of L with respect to x dot. That's going to equal mx dot, and delta x is going to equal t, and f is equal to mx. Therefore here q equals mx dot t minus mx. So m is going to equal, so q is going to equal m times the quantity tx dot minus x. And checking conservation, the derivative, the derivative of q with respect to t is equal to m times the quantity x dot plus tx double dot minus x dot. And that equals mt x double dot. So for a free particle here, mx double dot equals 0. So derivative of q with respect to t equals 0. So the conserved quantity is m times the quantity tx dot minus x. That's equal to a constant. And equivalently, m times the quantity x minus x dot t equals constant up to an overall minus sign. And here physically, this is the conserved quantity associated with a Galilean boost. And since a free particle moves as x of t equals x naught plus vt, we have x minus vt equals x naught. So m times the quantity x minus x dot t is essentially the mass times the initial position of the particle. And for the spatial translation symmetry, that's different. So for ordinary translations, x maps to x plus epsilon, and we have delta x equals 1, delta x dot equals 0. So then we could say delta L equals 0, and Noether's theorem gives P equals mx dot, that is a constant. So spatial translations give conservation of momentum, while Galilean boosts give conservation of m times the quantity x minus x dot t. So also adding here, total derivative to a Lagrangian does not change the equations of motion because we have the following: L, sorry about that, maps to L plus df dt, and that changes the action here by S maps to S plus f of t sub 2 minus f t sub 1. And with fixed endpoint variations, this boundary term does not affect the Euler-Lagrange equations. So, and pardon me here if I mispronounced anything. It's been a long day, haven't had enough coffee. But thank you very much. That's all for this problem, and have a great day.